You can't. So if you wanted to, go ahead. Go right ahead. Yeah. No, you were fine. You were fine. And I try to make sure that I don't get too technical.
Yeah.
I want to be correct.
I get that.
I want to be correct, but I want to
Testing.
present a simplified but correct explanation. And that's what this program does. It's kind of a big deal for me.
No, I get it. And that's all I'm doing is correct. It's just to give an opportunity to welcome
I might just do that. I didn't know if it was appropriate to have product placement in there, but if we're talking about,
everybody knows what's up.
yeah, I'm not going to change their fortunes by having their drink appear on my little program. Nobody's going to say, "Oh, Dr. Barth drinks Coke. Let's go buy some." Not happening. Not happening. What's that? Oh, okay. Okay. Fine. Right. Talk to the camera.
Yeah. You can watch while somebody else is talking. Right?
Right. And Scott and I chat back and forth when we do this.
Yeah, when you're talking, I know it's awkward. And if you can't do it, that's cool.
I usually work with a double monitor system at home.
Okay.
So
It should be somewhat.
there you go. Yeah, you need to accept their terms and conditions. There you go.
And this way you can keep it. What do you think that's what we're doing for a couple of guys in the camera?
You bet.
5 years ago, or 8 years ago.
Yes. And you know, the biggest result of the pandemic in terms of education is every teacher in the country is now trained to do remote education over the web. And you think about what that would have cost if some president had come along and said, my campaign promise is that within 2 years, every teacher in America will be able to do education online through various streaming services and bring education into every child's home independently. And so if the child can't come to school, the school comes to the child. If the government would have done that as an initiative, it would have cost $8 to $10 billion. It would have taken a lot longer than the 18 months it did take. Oh, yeah. Well, the first semester, when the university shut down in early March, I was doing podcasts and emailing. I was recording digitally and audio and emailing it to students. And then when I came back the next semester in the fall, they had purchased Zoom for us. And so we could all do it from Zoom. And so we started from scratch.
And a star that was very bright and didn't have any stars near it that would contaminate the image. We know that the primary mirror segments aren't aligned, so they actually act like 18 separate telescopes. And we expect to see 18 separate images, one for each mirror, that are a little bit blurry at this point because we haven't aligned or focused anything. And so we pointed at a bright star and we made a mosaic.
It's okay.
We actually took the near infrared camera and we took images in different parts of the sky. And then we looked for the 18 spots from the 18 different telescopes, if you will. And we were very excited to find them. And the 18 spots were actually fairly close to each other. So really everything was very close to what was predicted. We've identified which of the 18 spots is which mirror. At this point, we even know which ones are from the wings. And it turns out one of the wings, you can actually see those 3 spots are a little farther over. And that's sort of what we expected. So we've identified all 18 spots, and the next step is to make an array of them. And then we're ready to start called global alignment, which is when each of those 18 spots will start to be aligned and focused. And that's sort of the last step before we take those 18 spots and put them on top of each other to start forming a single star going through the 18 separate telescopes. That's the work that will be starting soon. We also took a selfie of the primary mirror. We took an image of the primary mirror, and that helps us understand the alignment of the telescope, especially the primary mirror, to the camera itself and the instruments. There's actually a special lens in the near infrared camera that you can put in, and it allows you to take a picture of the primary mirror itself. And in this particular case, one of the segments is pointing at a star, so that is the segment that lights up. But you can see the outline through the shadows of all 18 segments. And you also can see the outline of what's inside of the instrument itself. And we can see how well that primary mirror in the telescope is aligned to the instrument. And that gives us some initial confidence that the alignment looks good. And that's a good starting point for doing the alignment of the telescope. We have now gotten some data looking through focus, and we've been able to see that we don't see any surprises in the shapes of the mirrors that we're looking at. So far so good, but we do have a long way to go.
Okay. Hey, welcome, Scott. Nope, not hearing Scott right now. Scott's adjusting his mic.
Can you hear me now?
There we go.
Hear me all right? Okay.
There we go.
Okay, good. So if you guys didn't hear that, this is Scott Roberts from Explore Scientific and the Explore Alliance. And this is our 34th episode of How Do You Know with Dr. Daniel Barth. And the topic today is the James Webb Space Telescope. And
that's right.
There's been a lot of exciting activity going on with James Webb. Let me bring you on here. So we have, you can see that Daniel's background's a little bit different. He's in our studio today, and he's having a Coke. So
share a Coke and a scope.
And a Coke and a scope, exactly. So this is
if
not.
If they use that slogan, I want some money.
It's not. I'm sorry.
Not looking good for me.
No.
Oh well.
No. But anyhow, someone in the audience wanted to know where's your cool hat. So they were,
Oh, my cool hat. I have it over on the other table. I usually appear, as you know, with folks who are regular here, I usually appear from my home studio, which is in my
Right.
office at the world famous Barth Land Ranch and Observatory, high atop Round Mountain. And that people have asked before if that's a virtual background that I usually appear. No, that's my actual office with all the books and other things. And this week I was down to appear as a guest on one of Explorer's other programs. And
Well, we can say he was on.
okay, we can say I don't want to violate any rules.
Yeah.
Amazon
you can't
live
say
stream.
it on their channel that you're going to be over here, but
Right. It was
Vice
their
versa,
Amazon
yeah.
live stream, and they asked me to come in as an astronomy expert and help out and explain to people some of the benefits and advantages and cool features of some of their products, which was really fun to do because, as Scott knows, Scott and I met when we were both in the telescope biz.
that's right.
I was working as a telescope salesman. Scott was working for Mead Instruments.
Yeah, it was a
And,
sales manager back then. So
Yeah, back in the day, back in the early 90s. And I was selling scopes for a company out in California, and that's where we met. And we lost touch for about 20 years. And I walked into his office
then
one day, and he looked
shows up.
I know you. And indeed, it was really quite wonderful to meet a friend again after so many years.
Oh yeah,
And so
especially
here
out
we
there
are.
in Arkansas, right?
That's right. That's
would've
right. A
thought?
long journey. We both started in California and then ended up in Northwest Arkansas, which if you had to pick a corner of the country for two people to meet in again, after so many years, this would not be, I think, your hot pick.
Yeah, it's pretty good.
But Scott came out and put Explore Scientific here, and for his business reasons, and I came out to work for the University of Arkansas, where I train young teachers to teach astronomy and space science to children, because it's important, and astronomy needs to be the fourth core science with biology, physics, and chemistry, which are the traditional big three. So welcome to How Do You Know, folks. And this week, we're going to meet the James Webb Space Telescope. And the Webb telescope, I'm kind of assuming that it's going to be colloquially known as the Webb. You see it from NASA, the JWST, which just doesn't roll off the tongue. And Hubble Space Telescope System, everybody just knows it's Hubble these days, so I'm just going to call this like an old friend. We're just going to call it Webb. And Webb has been all over in the news. If you have been a space science or astronomy aficionado who searches up this sort of news in your news feed, Webb has been all over the place for the last year. And of course, Webb has reached its L2 point. It was such an amazing achievement, Scott. This telescope was folded up like an origami to fit into the launch vehicle. And they had to have something like 375 unique, one-time, no backup operations occur just right the first time in order for this to be a functional system. And they all went like clockwork. It's an amazing engineering achievement.
Yes.
And people really don't, when they see pictures of it, they really don't get how big and magnificent this telescope actually is. And we're going to tell you a little bit about it today. When it comes, why do we call it Webb? Webb was named for James Webb, who was one of NASA's very first administrators. Now, interestingly, he was not an astronomer. He was not a scientist. He was basically a corporate manager. NASA brought him on because he was the man who could get things done and manage large, complex projects. Because when you talk about space science, even back in the 60s when Mr. Webb was working for NASA, these space projects then as now, very complex. You know, thousands of people working on different parts, coming together, assembling them, and they have to work right the first time. In the 60s when James Webb was working for NASA, we were putting a lot of people in space. And this was new technology. And if the technology failed, people died. And we know the Russians lost astronauts. We lost 3 astronauts in Apollo 1 in a fire on the pad. We almost lost another crew with Apollo 13. We did lose astronauts in the Columbia disaster and the Challenger disaster. And so this kind of cutting edge technology, when you're putting people on top of a rocket and something goes wrong, people die. And when you're putting a multi-billion-dollar telescope on top of a rocket, no, people don't die, but I'm assuming that heads would roll if this thing failed and didn't work. But in any case, the interesting thing about James Webb is he said at that time it was all about manned exploration. It was about put a man in space, put a man in orbit, put a man on the moon. It was all about people in space. And James Webb came and said, you know, if NASA's going to have long-term viability, we need to have a balance between basically sending probes into space, what we now would call robotic space exploration, and manned space exploration. And at the time James Webb was working, it was very much a manned program. Today, we are very much a robotic space exploration agency. People in space, their role is much more limited now than it was, and we're much more heavily focused on the robotic mission. But nevertheless, Webb basically came in and he said, so far as I'm concerned, I'm not going to run a program that's just a one-shot program. If you want me to be the administrator, it's going to be a balanced program between human spaceflight and science that does the job for the country. Webb understood at the time that NASA was very much a political tool, and they were talking about beat the Russians, beat the Russians. It was a huge goal at the time. The Cold War was hot, and manned space was a big deal. And part of the reason, everybody who had military knowledge at the time understood if you can put a man in orbit and bring him back down where you want to, you could put nuclear weapons in orbit and bring them back down when you wanted to. So there was a unspoken part of the program back then that all our allies and adversaries got that the general public didn't really notice. But Webb said, no, we need to be a balanced agency. This is not just a political tool. And I think that makes him a great namesake for this space telescope. And during Webb's time, you're like, well, what did he do? Well, they had the first robotic exploration of the moon, the Ranger series. The first probes to Mars, the Mariner series. The first probes to Venus, the Pioneer series of spacecraft. And he actually initiated plans for the first space-based observatory, which decades later would become the Hubble Space Telescope, and more than 30 years of science exploration with Hubble. So Webb really, he helped guide and launch more than 75 different space missions. You think about that, the Webb telescope is one, the Curiosity lander is one, the Perseverance rover is one. Webb launched 75 space missions, an incredible accomplishment during his tenure. And so a great namesake for what we hope will be a great observatory. So let's just talk a little bit about the Webb. This, as I said, is a much bigger instrument than most people realize. Webb is 6,200 kilograms. That's 6.8 tons. This is a massive, massive instrument. And to think about taking something that weighs almost 7 tons, 6 metric tons, let's put it in orbit and then launch it out well past the moon. That's a terrific accomplishment. The primary mirror, 6.5 meters in aperture. You think about some of the more popular amateur telescopes. Compare it to a 12-inch Dobsonian. That's 300 millimeters or 0.3 meter. That has a surface area, a 12-inch Dob, which is a good-sized telescope, has a surface area of 0.07 square meters. Hubble, 2.4 meters wide. That's really large, and that's almost 8 feet. Has 4.5 square meters of surface area. Webb has 5.5 times more surface area than Hubble. You're talking about Webb has a diameter of 21.3 feet, 6.5 meters. It has 25 square meters of light gathering area. Scott, that's just enormous. You compare that to even some of the large 25 and 30 inch diameter gigantic Dobsonians that some people have. This thing is just amazing. It's larger than Palomar, Mount Palomar. The telescope there is a 5-meter telescope, the 200-inch, long time, the largest in the world. And this thing is not 5 meters, it's 6.5 meters. And I think pretty close to double the light gathering area of the Palomar telescope, which just gives you some idea of what kind of a size machine this is. It also has a focal length of 131.4 meters, or we're used to talking about, oh, this is a 1,000-millimeter telescope. This big Dobsonian has a 2.5-meter focal length. This thing has a 131-meter focal length. That's 131,000 millimeters. This thing is a monster by anyone's measurement. And rather like a Cassegrain telescope, it has a folded path for the light, which allows you to pack more focal length into a smaller package, relatively speaking. And of course, people ask, well, why do you have to have that really long focal length? Scott, you know, because Explorer sells lots of fine telescopes. The longer focal length you get, the more magnification you get. The aperture and the focal length together produce very fine resolution. Webb isn't made to look at nearby things. Webb is not made to be something like Hubble, which looks at things inside our galaxy for the most part. Yeah, well, Hubble looks at other galaxies, but Hubble really is designed to look in our galaxy and at things that are going on here and see them accurately. Webb is designed to look millions of light years distant. Webb is designed to look back not only in distance but in time, billions of light years away, billions of years back in time, to where we hope Webb will help us see an era of the universe when galaxies are first starting to form. There's a lot of mysteries, a lot of things we don't know. We have a pretty good idea how the Big Bang worked and how particles condensed out of the cosmic soup and these sorts of things. But there's a lot of mysteries on the more macro scale. How did the first stars form? What was their fate? How did the first galaxies form? How did dark matter condense out of the cosmic soup? How did the first black holes form? We know there are star mass black holes and there are supermassive black holes. Is there a reason there's no intermediate ones? How do black holes help young galaxies form? And are black holes necessary, or are they a consequence of galaxy formation? There's a whole lot of mystery that we just don't have the data yet. And Webb is designed with that tremendous light gathering area and that long focal length to be able to let us probe in detail these things from so far away. So let's take a minute and talk about those lovely, lovely gold mirrors. I've seen a lot of posts on social media where people have gone out and found gold hexagonal mirror tiles, and they've made little Webb murals on their walls at home, which I think is just a spectacular thing. If you search for these on social media, you'll find lots of images of them. And these mirrors are actually made of beryllium, which is interesting. Beryllium is a metal that before this was most often used in atomic reactors and atomic weapons. And beryllium is one of the super reactive metals. If you have beryllium dust or beryllium shavings, they'll react with oxygen in the air and catch fire. If you inhale particles of beryllium, berylliosis is a terrible lethal lung disease. And so you're like, wow, this is a really sketchy material. Why did you pick that? Well, the reason they picked beryllium is, first of all, it's very light. It's very light, and it's also extremely rigid. And we know if we're going to make a mirror, on Earth, we use ceramics, we use glass, because at the temperatures we operate a telescope in, glass is a very rigid and stable material. We can shape a mirror or the curvature of a lens to a fraction of a wavelength of light in terms of its overall perfection. And we know when we make that mirror out of glass or that lens out of glass, we know that the shape will maintain itself with great fidelity in the kind of temperature environment we're used to working in, from say 100 degrees Fahrenheit above to 0 degrees Fahrenheit, and even more extreme. But beryllium remains its rigidity down to cryogenic temperatures. Everybody has seen, I'm sure, glass fail under thermal stress. If you take glass that's warm, it's kind of a famous thing. If you're washing your car in the winter, don't pour hot water on the windshield because the thermal expansion will make the glass crack. You may have taken a hot glass and rinsed it in cold water and had it crack. Beryllium, really rigid, really stable, right down to near absolute zero. Its shape doesn't change, which means we can take these mirrors and shape them and know that the shape will be stable at these extraordinarily low temperatures at which Webb must operate. The mirrors are then coated with gold, and it's a very thin coating, basically a few microns thick. Why gold? Gold is the best reflector for infrared light, and Webb needs to work in the infrared part of the spectrum, and we'll talk more about that in a few minutes. So when we look at each of these mirrors, each mirror weighs 20 kilos. So each of those mirrors, the metal back of the mirror is about 45 pounds. And when we have the mirror assembly, which includes the gold coating, which weighs almost nothing, it's very thin, but there are actuators behind the mirror because we need to be able to collimate and adjust the mirror so all the mirrors work as one piece. The whole mirror assembly weighs about 40 kilograms. That's about 85 pounds. And their optical resolution, 1/10 of an arc second. Now, to give you an idea what we're talking about here, the moon is 1/2 degree wide. Okay, so that's 1/2 degree. Each degree is 3,600 arc seconds. So the moon is 3,600 arc seconds wide. This will get you down to 1/10 of an arc second. So on the moon is about 3,600 kilometers wide. It's also 3,600 arc seconds. So 1 arc second on the moon translates to about a 1 kilometer wide. That means 1/10 of an arc second. That's equivalent to an area from the Earth of just 100 meters on the moon. And that's better resolution than virtually any ground-based telescope can give you on a target like that. So a very, very accurate telescope system. And why did they pick these hexagons? Because hexagons, it's called tiling. If you're going to have multiple mirrors, you would want them to fill as much of the space. If all the mirrors were round and we stacked them together, think about putting a bunch of pennies together on a table and stacking them in a pattern. There's always gaps in between them. With the hexagons, there's no gap. They fill the space completely. In math, we refer to that as tiling. And the hexagonal mirrors, they allow those wings, the side panels, to fold back. And when they fold out, they can lock in position. And you end up with a finished mirror, which is completely covered, no gaps at all. If you're going to launch a system 6.5 meters wide into space, you want to take advantage of all that space for light gathering. And the hexagonal pattern lets NASA do that. The other nice thing about the hexagonal pattern, if you think about, here's a bowl shape for a telescope mirror, and you think about breaking that up into pieces, well, each shape is going to have a different curvature. The hexagonal pattern means that there are only 3 different curvatures, or if you want to think about it like eyeglasses, 3 different prescriptions that need to be ground. There are 18 mirrors, and if they did it with circular mirrors, they'd have to have 18 different prescriptions and curvatures. With the hexagonal pattern, they only need 3. And of course, if you're doing the same prescription multiple times, that means a lot less problem for manufacturing. So when we look at this, we've got a really fascinating mirror system. Let's take a look now at that really fancy sun shield. Throw some shade. This thing is 21 by 14 meters. That's bigger than your average tennis court. It's a little bit longer, somewhat narrower, but the area is comparable to a full-size doubles tennis court. Wow. And that shade is made up basically with very thin material, and it's coated with aluminum. It's aluminized much the way we aluminize a telescope mirror. And this material blocks out the sun. And people have asked me, but why do they have the multiple layers? Well, we're all familiar with the idea of fiber optics. And you're like, what's the connection here? Fiber optics are designed so that light traveling inside bounces, but never goes out of the fiber. It's called total internal reflection. Well, we take the much longer wavelength of infrared, where heat is. The layers of the Webb telescope are designed to essentially make like a fiber optic channel, a total internal reflection environment, so that the heat is carried out and radiated sideways away from the telescope. And we think about that. We've found a way not only to block heat from the bottom, but any heat that percolates through turns 90 degrees and radiates away from the telescope, where it cannot possibly affect Webb's camera systems. And it's really amazing. It's a material called Kapton, and it's a polyamide film developed back in the 60s by the DuPont people. And the nice thing, Kapton is stable from minus 270 Celsius all the way to 400 Celsius. For you non-metric folks out there, 100 Celsius is the boiling point of water. 37 Celsius is body temperature. And so when we're talking about minus 270, we're approaching absolute zero within a few degrees. And 400 is very hot. That's much hotter than your kitchen oven will get. So these layers are coated to help them reflect not only visible light, but infrared, which is heat. And this material is also designed kind of like ballistic armor, like Kevlar armor for the military and police authorities. That kind of armor only works because it won't rip. And these Kapton layers are sewed with what's called ripstop technology, so that even if a meteorite does penetrate, micrometeorite penetrates, Kapton being a film, think of a film kind of like clear plastic film that you put over food to go in the fridge, or plastic film that shrink wrap sometimes comes around products. If you tear that, it tends to just rip, because these films tend to rip just like they have a seam. Well, the ripstop technology means that even if a micrometeorite does puncture the sun shield, it's not going to go very far. The rip is not going to propagate and shred that heat shield and disable the telescope. So this is really cool technology. These 5 layers were deployed, and then they had separate tensioning cables to tighten them up just properly so everything stretches and stays right. It's not allowed to ripple, and of course it's not like a flag in the wind. There's no breeze out there to make it ripple, but they want to make sure that the layers are stretched geometrically precisely They maintain this very precise separation so they can exit that heat away from the telescope. The other question I get about Webb a lot is, well, why are they doing this infrared thing? And for that, let's think about a sunset. Let's think about a beautiful sunset. When we see a beautiful sunset and it turns all gold and then orange and then red, why is that? Why are we getting just those colors as the sun goes down? Of course, the sun gives us full spectrum light, everything from infrared to ultraviolet. But why at sunset do we just filter out all the colors but red? It turns out that the longer wavelengths, blue light is very short, red light and infrared light are very long, and guess what? Dust particles filter out blue, yellow, and green light very strongly. However, red light, because of its size in relationship to the particle size of dust particles, red light and infrared light pass through. So when we talk about looking far out in space, billions of light years back in time and out in space, why do we care about dust? Isn't space empty? Isn't space a vacuum? Well, no. Anytime we have a cosmic environment, something interesting like a galaxy or a star system, we have dust. As particles cool, we say, oh, here's a sun, it's very hot, and as things move away from that star, from the solar wind, they get cool enough that they can condense and become solid particles. The farther away you look, the more dust you have to look through. The only light that penetrates these clouds of dust, these cosmic clouds, is infrared light. And this dust, we've known about this for centuries. It goes back to something we call Olbers' paradox. Heinrich Olbers gave us a question in the, I believe it was the 1500s, and he says, well, if the universe is infinite, why isn't the sky always light? When the sun goes down, why isn't the sky bright everywhere? If the universe is infinite, every direction you look, you should see a star. Why isn't the sky brilliantly bright at night? The answer to Herr Olbers' paradox is quite simple. It's dust. Dust, both in our galaxy, in our solar system, and around galaxies and galactic disks, dust blocks visible light. And the farther out in space you look, the farther back in time you look, the more dust you must look through.
Yeah, right.
Yep, that's right.
Yep.
The only light that can penetrate that is infrared and near infrared. And so that's exactly what we've designed Webb to do, is to image in infrared light, which will let us see into these lovely dusty areas that will reveal to us what's going on inside the dust cloud. And
Daniel,
we've seen...
We have a question from Narina Falta from YouTube. She's watching on YouTube. She says,
Sure.
So what happens if, say, one of the mirrors is not accurate? Will the picture be messed up, or will they just remove that cell from the array?
You know, that's an interesting question. You know, Scott, that the Palomar has a couple of bullets in it.
No, not Palomar. I know
Yeah.
this one. It is McDonald Observatory.
Is it McDonald?
It's
Maybe I've got
McDonald.
the wrong observatory.
Yeah,
but
yeah.
Is McDonald
But
Observatory?
The answer you're about to give is very correct. You know, so
Yeah, somebody went up, and obviously a madman, and took a gun and said, oh, you're offending heaven by looking and, you know, peering up God's skirts or whatever, and blam, blam, and shot holes in it.
So
And all they did was pour pitch in the holes and paint them over black. To this day, if you have a mirror which is damaged, if you're an amateur astronomer and your mirror has a chip, you just paint it black. Now, we don't have the ability to do that. Webb is 1,000,000 miles away, but I'm assuming that if they had to, they could cant one of the mirrors so it would not add any light to the picture. Your question about what happens if the mirror is messed up, it effectively gives the telescope astigmatism. because the light from that part of the mirror array would not focus with the rest, and it would blur the image to some extent. They have a whole program, part of commissioning the telescope. They're going to image stars, and they're going to look at the different images where they're falling on the camera sensor, and they're going to adjust the mirror so they can bring all these star images into line precisely. And if one mirror was damaged, my assumption would be that they would take this mirror and they would just cant it, and so that it
That's what I
didn't
think they
contribute
do.
anything to
Yeah.
the image.
So it's just kind of aimed out of the light path.
Aimed out of the arts, right. It would be turned so it would be aimed.
There we
there's
go.
a-
There it is.
Is that
There's
McDonald
the picture.
Observatory?
That's
Oh, the guy
McDonald.
emptied his whole, he emptied all 6 rounds. Oh my gosh.
And apparently when he realized he wasn't busting the mirror apart, he went down to the mirror with a hammer, okay?
Oh,
And
good
started
Lord.
hitting the mirror. They pulled him off the mirror, I imagine with a straitjacket or something. And apparently he got a round off over the superintendent or something of McDonald Observatory.
Oh, Lord.
Just over his head. So no one got hurt,
No.
but they did think they lost this, multi-million-dollar telescope optic. And
Right.
it turns out that they lost less than 1% of the performance of that optic.
There you go. And it's an interesting thing, Scott. You know, and I know, if you're out doing astronomy in the dark with random people coming up to you, sooner or later you get some, shall we say, very interesting personalities come wandering in out of the dark and start asking you very interesting and strange questions. But yes, that's a brilliant question, actually, from our YouTube viewer. It is. It's an interesting question about what happens. And so we know about why we do the infrared light for Webb, and we think about this, and we realize that this is a telescope. This is a telescope that will take us to the next level. This is a telescope that will peer farther out in space, farther back in time than Hubble could go. And it has many times the light gathering ability of Hubble. It has significantly more resolution ability than Hubble. And it's designed for a very different job. But you think of some of Hubble's most iconic images, the pillars of creation, where they're showing new stars being ejected from a cluster, and they're trailing behind them these long streamers of gas and dust, which we can see the lovely contours with Hubble. With Webb, we'll be able, there it is, there's the pillars of creation, the Eagle Nebula. With Webb, we'll be able to look in, see what's happening inside that dusty cloud. And the cloud itself is very beautiful, and it's revealed many interesting things. But a cloud in and of itself suggests to the active mind, to the scientific mind, to the astronomer, what's inside. We've all looked at Orion's nebula, M42, and we've looked at it and gone, wow, this is great. Oh my gosh, look, I can see different layers of density. I can see the trapezium inside. But the question still lies, it's a cloud. What's inside? What's behind? What's beyond? Webb is designed to answer those questions that no amateur can answer, and currently no space-based observatory can answer. And we think about, oh, we can see the outsides of things. We can see the outsides of galaxies. Think of the Eta Carina, the Homunculus Nebula, that star that is nearing supernova, and it puffed off 2 great shells of gas. And Hubble has been watching this thing change for decades, get larger and thinner. And if you read about Eta Carina Nebula, people will say, oh, well, in another few decades, as the dust clears, we'll be able to see what the star looks like. Webb can look inside those sorts of nebulae right now, today, and watch what's happening inside the cloud as the cloud evolves. They don't have to wait. When we had the 1987 A supernova, we had to wait for decades to see, was it a white dwarf? Was it a neutron star? Was it going to be a black hole? We had to wait for decades as the cloud surrounding the supernova thinned and faded before we could actually see what was going on. Webb can look inside as these systems are evolving and changing. And so Webb can do things. It kind of really is a next level space-based observatory. One of the really great things too, they were so efficient at placing Webb in orbit that they only used a fraction of the fuel that they thought they would need, which means Webb has fuel for many more years of operation. And of course, we place this around the L2 point, and there's also questions about, gee, what's the Lagrange point? What's L2? Why is Webb there? And you know, Scott, we're going to save that for our next program on How Do You Know? We're going to talk about Lagrange points. And who was Lagrange? Lagrange. He was French and a lovely, brilliant man who made amazing discoveries. And like many people, we've talked about many historical figures on our program here, Scott. And his ideas were put out there, and the actual data to say he was correct, it didn't come until a long, long time after his death. But that's going to be our next program next week. We're going to talk about Lagrange points and how they work, what they are, and why are they so important to Webb, and what else lies at the hidden Lagrange points. And Lagrange points were kind of a staple of science fiction for years and years and years. There's a kind of almost a trope. Oh, there's an Earth 2, a planet that exists exactly opposite in our orbit, but exactly opposite us, so we can't see it because the sun's always in the way. That's the L1 point. And we'll talk about the rest of the exciting points, L1 through L5, when we come back next week on How Do You Know?
Awesome. There was a question about
Sure.
how much would one of the mirror segments from the James Webb Space Telescope cost. I can't tell you the number for just one.
I have no idea.
But we can figure it out. It costs roughly $8.7 billion for the optics. Yeah. Okay, that probably includes.
It's a $10 billion observatory.
Yeah, that probably also includes the secondary, 8.7 billion. So there you go.
Divide by 18, guys.
Divide by 18, but somebody just wanted an 8-inch. So, we could probably get it made for less, but
it would make a significant pile of cash. If it was all in $100 bills, I suspect you would need quite a number of big one-ton pickup trucks to haul it away.
That's right.
We did that activity. If you're interested, folks, the million, billion, trillion activities. The $1 billion in $100 bills is a 2.5 by 2.5 by 2.5 meter cube of neatly stacked cash. It weighs 10 metric tons, and that's $1 billion. And so if you're talking about 8.7, almost $9 billion for the optical system, that's 9 cubes of cash that are 2.5 meters on a side that weigh 10 metric tons apiece. That's the shock absorbers on my brain are bottoming out right now.
Right.
Yeah, it's a lot of money. On the other hand, knowledge is priceless, and I think part of the measure of the greatness of our civilization is that we're willing to make A, investments in our children in the next generation, and B, we're willing to make investments in pure science that helps us understand the universe and our place in it. It's different from practical applied technology where we say, oh, I want to build a better, more efficient system for delivering soft drinks, or I want to build a more efficient engine, or an electric car, or a better lamp, a better light bulb for your home that uses less energy. That's all worthwhile. But pure science, mega project science, is really kind of a monument to our civilization. The ancient Egyptians are known for the pyramids, these mega projects, and surely thousands of years from now, our civilization, our era, will be known for things like Hubble and Webb. They are our pyramids, they are our megaliths, they are these grand adventures and expenses where no one counts the pennies, but we all revel in the grandiose nature of the achievement. It really is an observatory for all mankind, and it's lovely.
That it is. That it is. All right. Well, great. Daniel, thank you so much. As you might remember, if you're watching out there, that tomorrow is Galileo's birthday. Okay. He would have been 458 years old. And
looking remarkably good for his age.
Yes, that's right. That's right. His fingers still, his middle finger's still out there. You can see that, if you're so interested, but that's not so, it looks like it's 458 more, or at least 400 years old or so. But I think he died when he was in his late 70s, something like that.
He was in his 70s when he passed away.
Yeah. So a very interesting character, and somebody that we'll be covering in the 84th or 83rd Global Star Party. And tomorrow night, it kicks off at 6 o'clock. We got a great lineup of speakers, as we always do. And so we hope you join us. But anyhow, you guys have a good evening. Thanks for tuning in on this Monday. Daniel, thanks for coming in and helping us out in the studio today.
Really nice being here where it's properly lit, and I have somebody to work the camera and the sound and everything for me. This is really luxurious. I've enjoyed my time here today.
Videographer and armchair director back there. He's handling the whole studio back there and does quite a great job. So thanks,
That's right.
Thanks again, and we will see you tomorrow. And until that time, keep looking up.
Good night, everybody. Thank you. Am I out already? Almost.